Section 1.6 Rules of Inference. We consider this example. If you have a current password, then you can log onto the network. You have a current password, therefore you can log onto the network. The first two propositions are called premises. The last proposition is called the conclusion. The argument is valid when the conclusion is true, provided that the premises are true. Argument form. If P then Q, P and therefore Q. The argument form is valid if any time when the premises are true, the conclusion is also true. We can figure this out. We can figure out that this argument form is valid by considering the truth table. If you look at the form, there are two variables only, P and Q, propositional variables P and Q. So we construct a table with a column for P, a column for Q. In these two columns, we put all possible combinations of true values for P and Q in standard form. TT, FF for P, TF, TF for Q. And then we must construct a column for each premise and for each and for the conclusion. P and Q, we already have columns for P and Q. So we have a column for the conclusion, a column for one of the premises. We need a column for the first premise, if P then Q. So write a column, label it with if P then Q, and then fill out the values. Those truth values come from the definition of conditional proposition. We know that conditional proposition is true only when P is true and Q is false. It is false only in this case, when the first variable is true, the second variable is false. Now, go over the values of the premises. The premises are if P then Q, and this Q. Anytime when both of the premises are true, the conclusion must be also true. Then the argument is valid. And the premises are true only in the first row. The conclusion is also true. And the conclusion is Q. So we'll look for premises. Both premises are true only in the first row. And the conclusion is also true. In the second row, not both are true, not both are true. So this argument form is valid. It is called modus ponens. In general, an argument form is a sequence of compound propositions involving propositional variables written this way or this way. P1, P2, and so on, Pn, and therefore Q. The argument form is valid anytime when all premises are true, the conclusion is also true. If there is at least one exemption, then the argument form is not valid, and we call it fallacy. Determine if this argument form is valid. If P then Q, if Q then R, and therefore if P then R. Instead of building a table which will have should have 8 rows, because we have 3 propositional variables, P, Q, and R, we can argue this way. Let both premises be true. If P then Q, if Q then R. We have to show that the conclusion if P then R is also true. We consider 2 cases. The variable P is either true or false. In case 1, P is false, because P is false, the conclusion if P then R is true regardless of the truth value of R. This is from the definition of conditional proposition. In case 2P is true, since if P then Q is true, Q must be true, and since if Q then R is true, R must be true, which means that if P then R is also true. So if we prove that in both cases the conclusion is true, this makes the argument valid. The next example, determine where the argument is valid. If not R, then not P, R, and therefore P. We'll see that this is a fallacy. To see that, we have to find a case when both premises are valid, but the conclusion is false. And we can select its values. R true, P false, and want to false the conclusion to be false. Now R is true, not R is false, so this is true. Conditional proposition. R is true, so both premises are true, but the conclusion P is false. So I prove that it is a fallacy. 7. Example 7. Determine that the argument is valid. P and not P, and therefore Q. We have 2 variables, so we can construct a table. 2 columns for P and Q, fill those out in standard order. And then we have not P here, so a column for not P, fill this out. FF to true. And then a column for the premise, P and not P. P and not P. And true and false is false. True and false is false, false and true is false, false and true is false. So this is the column for the premise. And we don't have a case when the premise is true, because we cannot find a row in which all premises are true but the conclusion is false. There is not a counterexample which makes the argument valid. Rules of inference are short valid arguments. And these are the well-known rules of inference: modus ponens, modus tollens, addition, P and therefore P or Q, simplification, P and Q and therefore P, conjunction, P, Q and therefore P and Q, hypothetical syllogism, we proved that this is true before, disjunctive syllogism, P or Q and therefore, P or Q, not P and therefore Q. To prove the disjunctive syllogism, we look for a counterexample. In any counterexample, Q must be false, not P must be true, and P or Q must be true. Because not P is true, P is false. Now, Q and P both are false, therefore P or Q is false. So we cannot find a counterexample. In a counterexample, P or Q must be true, not Q must be true, and the conclusion must be false. Because there is not a counterexample, the disjunctive syllogism is true. Argument. Using rules of inference to build two arguments. Show that this argument is valid. Not P and Q, if R then P, if not R then S, if S then T, and therefore T. Step 1. Not P and Q is true because it is a premise. We apply simplification. We conclude that not P must be true. If R then P is given as a premise, now we can apply modus tollens and conclude that not R must be true from these two. Now we apply now use this premise. If not R, then S. This premise and the previous true proposition apply modus ponens. The conclusion is S is true. We have this premise given in the example. Now apply modus ponens, S if S then T, and therefore T. And this is the conclusion that we wanted to prove. So the conclusion is true. When all premises are true, we prove that the argument is valid. Resolution proofs. This is a proof technique that depends only on the following valid argument: P or Q, not P or R, and therefore Q or R. This can be proved. This argument can be proved by considering this table with 8 rows. Fill out all columns for P, Q, and R in standard order, and then fill out the needed columns using the definitions of negation, disjunction, and then go over the premises. The premises are in these two columns. Anytime when both premises are true, the conclusion is also true. TT, also T here, TT, and we have T in the conclusion, TT, T in the conclusion. In the remaining rows, we don't have T's for the premises. So anytime when both premises are true, the conclusion is also true, which makes the argument valid. A clause consists of terms separated by ors, and each term is a prepositional variable or negation of a variable. So this is a clause because we have negation of a variable, and then they are separated with an or. This is a clause, this is a clause, this is a clause. But this is not a clause because we have conjunction here. This is not a clause because we have conditional preposition. A direct proof by resolution proceeds by repeatedly applying the resolution argument to pairs of statements to derive a new statement until the conclusion is derived. Every time P must be a single variable, but Q and R may be clauses. We are talking here about this. P must be a single variable, Q and R may be clauses. And what is formally done here? We eliminate P and not P, and we take disjunction of what remains. Q remains here, R remains here, we take disjunction. So formally it is very easy. Disregard P and not P, and take disjunction of what remains, Q or R. Example. Prove that the argument is valid using resolution. We have 1, 2, 3 premises and one conclusion. All the premises are of this form, the form of a clause. So far, premises are clauses. So we can, in each step, we select 2 clauses. Select 1 and 2. Eliminate P and not P. What remains is Q or R. So Q or R is a true preposition. Denote this by 4. Now we have 1, 2, 3, 4 true propositions. We can select any two of those 4. If we select 3 and 4, so this 3 and this 4, we can eliminate R, not R, and we conclude that Q or S is true. But Q or S is the conclusion. So we're done. In some cases, the given clauses are not, the given premises are not clauses. In that case, we try to replace them with clauses. P or Q is equivalent to Q or P. If P, then Q is equivalent to not P or Q. So if we get this premise, we can replace it with a clause. The negation of P or Q is equivalent to not P and not Q. So we can replace this negation with two clauses. Two premises, each of them will be a clause. And similarly, the negation of P and Q is equivalent to not P or not Q, according to the De Morgan law, and this is a clause. P or Q and R is equivalent to P or Q and P or R, so we can replace this with two clauses. This equivalence is called distributive law. In this example, prove that the argument is valid. We replace this with two clauses according to the distributive law, the first and the second. You know this conjunction is true when both prepositions before and after the conjunction are true. So we can write 3 and 4 as clauses, and 2 can be replaced with not P, not S, two clauses. So instead of two premises, we'll have 1, 2, 3, 4 premises given. Each of them is a clause, and we can apply resolution to any two which we select. We select 3 and 5. 3 and 5. P, not P, they disappear, not Q remains. So we derive not Q, and not Q is just what we want. This is the conclusion in example 2. So we're done. Example 3. Prove that the argument is valid using resolution. We replace one with not P or Q. We denote this by 3. Now 2 and 3 can be used. Eliminate P and not P. Derive Q or Q. but Q or Q is equivalent to Q, so we obtained the conclusion in example 3. Next, we consider rules of inference for quantified statements. These rules of inference: for every x p of x, and therefore p of c for some element c from the domain of x. This is called universal instantiation. P of c for arbitrary c from the domain, and therefore for every x p of x, universal generalization. There is an x such that p of x, and therefore p of c for some element c. Existential instantiation is the name of this rule of inference. In the next row, p of c for some element c, and therefore there exists an x such that p of x. Existential generalization is the name of this rule of inference. For every x, if p of x, then q of x, p of a, and therefore q of a, universal modus ponens. In this example, we assume that this statement is true. For all positive integers n, if n is greater than 4, then n squared is less than 2 to the power n. Show that 100 squared is less than 2 to the power 100. We use universal modus ponens. Just select n to be 100. Use universal modus ponens and you derive the conclusion.